I am now going to go through a bunch of slides on XML, XSLT, model-driven software development, and some stuff about research and languages. So, XML and XSLT. The context is dynamically generated HTML driven by some host language. So we want to think about programs that print HTML code. So for example here, bottom right, we have a program print prices. We call it will print HTML code such as the one above here. So given a list of items, items have a name and a price. It's going to produce the HTML code here, which when viewed in an appropriate browser or something like that, it's going to look like a list like this. So similar technologies are something like JSP and ASP.NET. So the point here is that this is very much similar to what we've already seen with program generation and extend and so on. This is awful code to read and maintain in print prices, but the good thing about it is that it can generate many different kinds of HTML from the same from data. So we do get a lot of reuse. So how can we make this code here better? We use templates. So the typical way of using templates is that we write then directly what we want and then have a special syntax to escape into the generator. So we can say for all of the things in our list, do lists with name and price. And now we have a structure that is easier to read and easier to work with and easier to maintain. Again, JSP and ASP.NET. Now, the thing that we want to think about in the concept of this course is, of course, program generation. So we do the same just with programs. We have something that generates or we want code like this, something that prints an output, maybe calling printf in a C program. And we want to, this print function is going to be different for every list of items. So we're going to generate it. And for that, we use a generator, like the one we have on the bottom here. If you wanted to do the same, so this is using a template syntax sort of similar to extend. If we instead we wanted to use XSLT, then it would look like this. So, and this is in fact this XSLT file here will generate precisely this kind of output here. So this is what it really looks like. So for each of the items, take the name and the price, and that's it. So very similar, but a bit different. So template-based programming, actually rather than JET, this should say well, very simple. So template-based program, this is covered by Fowler as well. In the pure template-based versions, this is hard to work with. They're good for quick and dirty code generators. So we haven't really worked so much with template-based programming because it's not anywhere as good as extend. Anyway, so they're easy to quickly write, but they have very limited compared to full compiler. Language workbenches, on the other hand, like extend, powerful, but also more complicated. If we build templates into the host language, like we do for extend, then flexible, but we must understand framework and the language. XML and XSLT, fairly easy to use for the right tasks and relatively simple. So it is something we can consider using. A small example of using them for program generation. So this is generating C code for state machines. So we want to generate an enum that lets us encode different names of signals. So we have upsig, downsig, and then a special value called maxsig, which is the largest value. This is again some C programming, a bit of clever use of the way enums work. So it doesn't matter so much. Then we have something for converting the value of an enum, which is a number, into the name. So we want to generate this function as well. So this is just a switch on the value and we return it. There's no error handling here. We could add that, of course, but we haven't. And so the point is that the model we generate this from, so here with XML, we in fact write the model directly. We don't have a syntax. We don't have a DSL for writing our model. We directly write the model using XML. And of course, now, since we do that, then when models have inter references between them, then we have a bit of a problem, but that's another story. Like if we have the difference between an abstract syntax tree and a semantic model. A semantic model, things that are same are connected. We don't have that the same way in XML. Anyway, here we have an enum. The name should be hooked signals. It should start with the value 1 and include these two elements. We can also, in fact, what we really want here, since this is C code, then we want to generate an H file and a C file. And so we want the H file containing the enum and a declaration of the function, and then the C file containing the actual declaration. So what does this look like in XSL? The XSL file transforms the XML. And so we say, oh, the first file we want to generate, that's the .h file, which is then the name.h. And there's some stuff here that I'll cover afterwards. And this, so result documents means write into one file. And here you have the same thing for the other file. So this is how in XSL you generate different files. Looking inside it, what we want here is to generate the code on the top right here. So we have enum, the name, open brace, so that's the open brace up here. And then we say, we have to be a bit clever here because on the first one, we want to do something different than for the next ones. And then we have the last stuff at the end. So what we want to do differently is that we want to say equals something so that we know what the value of the first enum element is. And for the preceding ones, we want to do something different. So here we say apply templates inside it. For the first element, do it with mode first. For all other elements, do it with mode next. Here we have sort of a declarative way of expressing how to apply templates. Apply to all elements for which this is true, that's the first one, and then apply it to all elements for which it's true that the position is greater than 1. So that's in fact a declarative notation for matching templates and for generating code. Down here at the bottom we have the templates. So we say if it's an element and mode is first, then we insert the name, and then if there's a start, then we insert the start value. Otherwise, it's the next one, and then we just put it in there. So that's the basic example of using XML. How does this work? What's beneath it? This is just a quick overview. I mean, we could basically have lots of classes about this. So XML is a markup language, fixed keywords and grammar. It's designed for meta markups, so markups of any kind of data. It's sort of an ancestor to HTML, which was too flexible. No one could figure out how to use it. So XML, start and end tags, attributes. It has to be well formed, so matching tags. XHTML is a special version, HTML version that obeys the XML spec. It needs to start with the declaration of version and character set. We can put comments and all kinds of other things in there. When we design our language using XML, we use XML as a kind of language. Then we directly use the XML to write, as I said before, the semantic model. But then, of course, we also need to think about how to make it easily readable for humans. So sometimes we might want to deviate a bit, but here we're sort of caught in you having the same representation for both what the human uses and for what the model is. The concept of a model-to-model transformation that I'll talk about later might come in here. So we might start with one model that is convenient for the human to write and then transform it to a different model that is convenient for the processor to use. So we might work with multiple models that we transform between them. The XSL is the language that we use for transforming an XML document into a result document according to the XSLT specification. And XSLT is what we use to generate output from templates, and then there's this language XPath that we use inside XSLT to navigate the XML document, to collect information, and to do computations. So what elements are there in XSLT? Well, if there's some text, then it just becomes that text. We have value of, which picks out values from the XML document, and we have for each, which is the generate a for loop, we can go for each some XPath expression that evaluates to a whole bunch of things, for example, a subnode in the XML document or something else. For each of those, generate what's in between the two. And we can also, there's some clever things you can do if you for computing names of attributes and computing other things using XPath. So understanding XPath is really important for this. Again, it just means that there are many places where you can compute things to control what the XSLT style sheet is doing. What it does is to navigate somehow the XML. So for XML here, this is an example from a book that I used. So we have a document that has an element with the TV guide, has channels, and each of those might have names and programs and stats and so on. So basically the same thing as you've been seeing before for models, except it's always tree structured. So if there were references between two different programs, two different channels, we have to represent them maybe as names or as paths that it's document slash element slash channel 7 or whatever. So that makes it a little bit more complicated. XPath, basically, it's something, it's our expression language that we use to query XML data. To query the XML data, we can write slash the node, root node, which is out here the document here. We can write star any element. So document slash element slash no, sorry, here. So TV guide slash channel slash program slash star means all of these three elements down here: start, duration, and series. And there are also different kinds of matching to match any text or some specific text. Slash is used for nesting, and there's alternatives as well. So we could write TV guide slash channel slash program slash start or duration, which would match any of these two nodes here. So lots of, again, more declarative notations for navigating these. In the XSLT, this general structure we have is that we have a style sheet, a set of templates that are defined. Say in template, here's what my template matches, and which would typically be one of the nodes here, like TV guide or channel or whatever. And then templates are then used when they are applied. So we then apply the templates, and we can say that only specific templates by controlling the match. And we always start with the root templates. And one template can use another one by calling apply templates. Now, if we're inside the channel here and we do apply templates, then the templates will be applied inside this one, unless we specify something else using XPath. And there are different ways of controlling it, like mode, which is, oh, now we're doing one thing, there might be something else. And that basically there are two different, we call it push and pull way of using this. So we could follow the XML document structure and generate code as we're going through it, or we can extract data from it, saying, oh, now we need information about programs, and now we need programs information about names of channels afterwards, and then extract it from the XML document. So that's the push and pull. Push is we follow the structure, and pull is we extract data from the document. We also have conditionals in there, like we can do an if, XSL if, or choose is like a big switch thing with the multiple cases. And there are all kinds of conditions we can write using XPath. Again, in fact, a fairly advanced declarative language for specifying which kinds of attributes we're interested in, which kind of nodes we're interested in. Variables are something you can use to gather information as well. They're immutable, so we can use them to gather information in part of a processing of a template, but it doesn't change while we're processing it. So we can use it to count things, for example. But we can use other kinds of things like the position of a node or summing up things, and we can also do some recursive programming to get values that change as we're processing. So that was the very quick overview of XML and XSLT, and now I'll proceed with model-driven software development. So The goal of model-driven software development is to have software factories, which is basically what we've been talking about in the course, but maybe a more industrial, more structured approach to it. So we want automation to get increased development speed and better software quality. We want separation of concerns to make things more manageable. We want a software product line, which is a basis for creating many different software products. So reusability and capturing the expert knowledge that we do have. And we want it as a program abstraction to better manage the complexity of our system. Model-driven software development is that we think about models being abstract as an abstraction, allows us to think better about it, but formal. So we want to define precisely, and they're part of the software. So we might use a domain-specific language defined by a meta model to program it, and we might have a domain-specific platform, which is the target we try to reach. So we specify the formal model using the DSL. We automatically transfer code to the platform and supplement with manually written code as appropriate. Now here are some figures from, here's a figure that is intended to illustrate model-driven software development from the reading material that I gave you. And now here's an annotation that brings it a bit closer to what we actually mean by this. If we take XX, for example, so if we look at the figure, this is the original program, which we then refactor to use model-driven software development. And we can then write application models using our DSL, whatever DSL we define, so that might be state machines or whatever. The DSL is transformed, is specified using a domain-specific language, defined in xtext when we use xtext, and transformations are done using the extend generator. We might have some plugin code for using generation gap for individual code, and then we have a platform, which is the target framework that we use. No, sorry, that's of course the generated code here. So this is the code that we generate from our DSL, so that it uses the reusable code here. Now, these annotations are just annotations. This is a very general way of thinking about software development using domain-specific languages that applies to many other things than xtext. Xtext is just there to make it easier to see what's going on. If we were to use XSLT instead, then we use XML documents to specify the application models. XML is our domain-specific language as well. We might use the Saxon transformation engine to use our XSLT transformers. Our individual code might be handwritten C code that interacts with generated code from XSLT, and a bunch of C libraries for defining state machines, for example. So many different understandings of the same concept. So some of the basic concepts that we use in model-driven software development. Model-driven architecture is a standard for model-driven software development that lets us reuse architecture tools and generators based on UML. I think it is large and complicated and difficult to work with, but in some industrial applications it has been useful. I'm a bit skeptic personally, but it's there as a standard. We then differentiate between different kinds of models. Platform independent models, so this is where we're still working with things in a very general way. So a state machine would be an example of a platform independent model, and then we might have a platform specific model that we generate from the platform independent model by doing model-to-model transforms. We could also have other models in between. So for example, we could imagine generating the state machine model from a different kind of model that was even more general, maybe even more declarative, saying, we want some kind of safety that when the user presses the emergency stop button, this should happen, and we could then implement that using a state machine. So we could have transformations between different models and thus reuse, which is the key thing here, reuse of models and transformations in a structured way. We work with what we call architecture-centric model-driven software development, where on the left we have our application, where we have a design model that describes it. It's modeled using our UML profile or domain-specific language. The generator then generates all of the infrastructure code in which we can nest the business logic code, which is the interesting code that we want to write by hand because it does something useful, not all of the nasty move data back and forth between different layers stuff. And again, this is supported by an infrastructure, which often could be a set of components or some sort of platform. When you think about modeling in the context of Xtext, again, here we have a general sort of schematic, a model of what it means to be modeling, if you want. If we again take that specifically for Xtext, what does this mean? So our abstract syntax, we can start with that. Here is an Xtext grammar, or maybe BNF, or but here, when we talk about the abstract syntax, it's like any kind of syntax we might want to use. So we could write that using Xtext, but there could be many different abstract syntaxes. Typically, this is a BNF kind of thing. The concrete syntax is then what the syntax really is. So for the state machines, we could have an abstract idea of what the syntax should be, but when we implement it in Xtext, we get the concrete syntax. So with Xtext, we typically don't make the difference, but if I was to write a BNF on the blackboard, that would be the abstract syntax, and the concrete syntax would be Xtext. We can implement any kind of DSL using Xtext. The static semantics is name references, which is typically checked by extend, but there might be other things we need to add. The semantics is what does the generated code do? Extend doesn't really have support for expressing that, but of course in the end the generated code will do something. The domain that we can use with Xtext is anything, so it might be state machines, for example, or whatever. And the formal model is whatever it is that we are using in behind. So that might be, which is an instance of the meta model. So that's the semantic model instance. So that's the DSL program. And of course, it's an instance of the meta model, which is also what Fowler calls the semantic model. So here again, the semantic model is composed of static semantics, abstract syntax, which is typically then concretized, and it's an instance of again the meta model, which in this case is the Xtext language. Again, we can play with XML and XSLT. So suppose that we wanted to do state machines with XML and XSLT. So now I'm being more specific. Our meta model here is XML schemas. An instance of this is our state machine XML schema. I didn't talk about XML schemas, by the way. So they're a way of specifying the syntax of an XML document. And the abstract syntax is whatever we want the XML schema to look like. And the concrete syntax is the XML. That's what we use to write it. Our DSL is then a state machine specification language, which uses XML as a concrete syntax. The domain that we could see for state machines could be event-based reactive systems. Again, formal model is the concrete program, so it might be a cooking hood or whatever. And semantics, again, sort of unspecified in this approach, is what the states are just when an event arrives. Transformations is different kinds of transformations, again, from a model-driven software development point of view. Looking at it with our Xtext classes, a transformation is specified using or takes a source that is transforming, maybe a cooking hood or whatever, based on a meta model. It might be the Xtext. Xtext is not good at model-to-model transforms. It just doesn't work so well. It would be generating a new EMF model and then transforming that again. But it's sort of clumsy, so I'm not going to talk so much about it. The model to platform transform, that's the extent. That's what transformed it. And then we generate a bunch of Java code, which is the implementations. And in the end, we get a product, which is a state machine implemented in Java. composed of the generated code, some non-generated code, um, which might be some Java code that I write by hand for having a main method or integrating to other parts, and then the platform, which is that might also be external code, sorry, and then the platform, which is like the machine and the state and the other generic classes. From the point of view of XML and XSLT, transformations are specified in XSL. The formal model is written in XML. The meta model is a schema, so that might be an XSSD file. Model-to-model transforms works better with XML because we transform one XML document into another one and just keep going. So if we used enums for state machines, then we could transform from the state machine to the enum XML document and then generate the enums based on that. Again, in the end, we get a product which is a state machine implemented in C, composed of some generated code, some non-generated code, like what actions do we want to take, and a platform, maybe some generic stuff for finite state machines. So how do we compare model-driven software development versus domain-specific languages? So model-driven software development is sort of an industry approach to domain-specific languages. It's heavy on tools. There's a focus on UML-based models and graphical UML syntax. So I've heard some people refer from the MDSD camp refer to domain-specific languages as unstructured, which I don't think is fair. But in a way, the key point is that if you do model-driven software development, then everything is UML and models. Whereas DSLs are maybe a bit more ad hoc, but also offer you many different ways of doing things and can give you some very powerful abstractions. This model-centric approach is definitely useful for long-living artifacts because you're very careful about how you model each thing and how they relate to each other. We have the whole Eclipse system is built around the idea of model-driven software development, MATLAB and Simulink, SCADE, which is used for lots of safety critical systems, nuclear power plants, airplanes, whatever. All model-driven software development principles apply in different ways, not necessarily UML, but the same kinds of principles. And we have lots of interest in it in the robotics community, and I'll come back to that a little bit later in the second part of this presentation. So I'm going to just take a short break, which might slightly disturb the way this proceeds.